Okay, so on this example, it wants to take the derivative of 2 to the x. Yeah, this notation is just another way of saying the derivative of. We could say it, yeah, I don't want that to be confusing to you. Or we could say 2 to the x derivative. What is it? What does it equal? What does it equal? Either way, it's the same thing. This way or that way. They're just two different ways of saying the derivative. You can put ddx in front, or you can put a big prime on it, whatever. Okay. So the question is, what is the derivative to this? You can see the answer here. Let me help you. So give you the rule. So we know the derivative of e to the x, right? E to the x derivative is just e to the x. That's why we call him our favorite, because he does nothing. We wish all the derivatives did that, right? He does nothing. Why does he do that? Because E is the perfect number. That's part of the specialness of E. You know what I mean? Like pi is a special number, 3.14159. It goes on and on. It does a very specific thing with circles. It's the ratio of the circumference to the diameter of any circle. Anyway, we're not doing geometry, so enough said. It's a special number. We just discovered it as part of the created order that anytime they found it, ancient Egypt, I think it first turned out, they were measuring around circles and across circles, and they were dividing those numbers. They kept getting this 3.14 number. Even big circles, tiny circles, they just, no matter, they go measure around, measure across. Anyway, too much history there. E is another special number, and it's 2.17. Wait, no. All of a sudden, I can't remember whatever. It's a 2 point. I can't remember. 2.17. Yeah, anyway, whatever it is. Maybe it's not 2.17. I can't remember. It's two something. How about that? You can look it up. It doesn't matter. It's a special two something special number, just like pi is a three something special number. Now, what's special about it? For pi, it's all about circles. For e, it's some more advanced calculus stuff, and this is the first thing we see. E is the perfect number to be his own derivative. He's the perfect number to be our favorite so the derivative comes out exactly the same as it started. Now, okay, so what? So why are you telling me this isn't E, Mr. Aaron? Yeah, I gotcha. But that's the point. If you have any other number, like say 2 to the x. Now notice, by the way, that is a lot. These are very similar, right? They both have x in the power, and they both have a number in the base. So their derivative answers should be kind of the same, right? By the way, they're not. I think it'd be helpful at this point to say what they're not. What if we had x squared? What would be the derivative of x squared? Well, we know that. You just bring down the 2, you subtract 1 from the power. It's 2x to the 1 or just 2x, whatever. Right. So that's when x is in the base. But now we have x up in the power. Notice. That's what's different. These are called exponential functions when x has climbed into power. So this right here, when x is not in power, this is just a polynomial. Call that, polynomial. Whereas these guys are exponential functions, meaning exponential doesn't mean the e. It could be, like I'm saying, not only the e, but also the 2. You don't have to have the e. Exponential means x is in power. Do you see what I mean? X is up here in power, X is up here. It doesn't mean you got E in the base. I know we kind of think that, but that's not right. It just means X is in power. Exponents are powers, right? Just means you might think, well, these have powers, right? But specifically, we mean X climbed up there into the power zone. So when X is in the power zone, we call those kinds of functions exponential functions. And when X is just in the base and there's powers, we just call those polynomials. You already know the rules for how to take those derivatives. Just bring down the number, subtract 1 from the power. There we go. But now we're talking about what happens when x gets in the power. That's different than x in the base with numbers in the power. Now we have numbers in the base with x in the power. That's a more powerful thing when x itself gets up there in the power zone. Okay, and what's the derivative rule? Well, for e to the x, it does nothing because e is that perfect number to do nothing. But 2 to the x or any other number, since they're not the perfect number, what do? Well, at first they'll do the same thing as e to the x, meaning nothing. But because they're not the perfect number, you've got to multiply by the natural log of that base. And that's the answer. They put it in the front, you can put it in the back. It doesn't matter. So that's it. That's the answer. The answer to this is you go 2 to the x, right? Because it's you should think in your mind it's like e to the x. Just think, well, it's like e to the x, and that's my favorite derivative. E does nothing. So you're right. At first, it does nothing. It just repeats itself. But then because it's not the perfect number, because this isn't e, the perfect 2.7. Oh, there it is. Mine again. 2.71828. Blah blah blah. That's what e is. Anyway, I don't know. I forgot it for a minute. Anyway, E is the perfect number. Two is not that perfect number, so he's gonna need a little adjustment. And what it is, it's the natural log. You might wonder where the natural log come from. Well, it's a longer story. I could office hours. I'd love to prove to you where this all came from, show you the details. I think it's super fun and interesting, but not gonna do it on this video. I'm assuming that you mainly just like this here, and I'm just trying to get my homework done here. Gotcha. All right, I've gone long-winded enough as it is. But I'll just say ln is a base E function. It's not a surprise there's an adjustment with E with two, and enough said. That's our answer. So my point is when your base, when you have x in the power, it's called exponential function. If the base is e, he's our favorite, he does nothing. If the base is any other, say this was a 10, or let's go 13, whatever, then it's going to be 13 to the x, natural log 13. You have that little adjustment because you didn't have the perfect number. So he almost does the same thing as e to the x, which is nothing, just repeats himself, little mere reflection. But then there's a little adjustment because it wasn't the perfect number. And it's always ln of that base because ln, remember, is the natural log, which is the inverse of the base e. All right, enough said. There we go.